Taylor and Maclaurin series. First, let's start with a definition of a Taylor or a Maclaurin series. We'll start by supposing that a function f can be represented as a power series, as shown here. Now, let's observe what the derivative of f is. When you take the derivative of the constant c0, you get 0. The derivative of c1 times x minus a is just c1, plus the derivative of c2 times x minus a to the second power. We're going to bring the 2 down here, subtract 1 from the power, and the derivative of the inside is 1. The derivative of the next term will be 3 times c3 times x minus a to the second power. Derivative of the next term, etc. Let's go ahead and take the second derivative the same way. Derivative here is 0. Derivative here is 2c2. The derivative here is going to be 3 times 2 times c3 times x minus a to the 1. Derivative of the next term is 4 times 3 times c4, x minus a to the second. And again, this continues. The third derivative here is 0. The derivative here is 3 times 2 times 1 times c3, plus the derivative of this term is 4 times 3 times 2 times c4 times x minus a to the first power, plus etc. Now we'll just do one more. The fourth derivative starts off with derivative of this, which is 0. And the derivative here is going to be 4 times 3 times 2 times 1 times c4 plus the rest. Now, we're not showing all the rest of the terms because it's not necessary. What we want to do is develop a pattern here. So what happens if you plug the number a into the function f of x and all of the derivatives shown here? We know that f of a is going to be c0. And this is because when you plug an a into all of these terms, a minus a is going to be 0, and so all of these terms cancel out. F prime of a is going to be c1, because again, when you plug an a into here, all of these are going to cancel out. F double prime of a is going to be 2 times c2 for the same reason. The third derivative evaluated at a is going to be 3 times 2 times 1 times c3. And the fourth derivative evaluated at a is 4 times 3 times 2 times 1 times c4. And this pattern continues. So if you were going to make a guess, would you be able to guess what the fifth derivative at a would be? Well, if you look at the pattern here, it seems that it would be 5 times 4 times 3 times 2 times 1 times c5. And I want you to notice that this is the same as 5 factorial times c5. And the previous one can be written as 4 factorial times c4. This one can be written as 3 factorial times c3. Here, 2 factorial times c2. 1 factorial times c1, and the first one here can actually be written as 0 factorial times c0, and this is because 0 factorial is defined to be 1. So it seems that we have a formula. The nth derivative evaluated at a appears to be n factorial times Cn. But if you turn this around, you can solve for Cn and say that it's equal to the nth derivative evaluated at a divided by n factorial. And this allows us to solve for the constants in the original power series. So remember, the CNs we are referring to are these numbers here. So now we have a formula for these numbers. And we're going to represent that in the following theorem. So theorem says if f has a power series representation expansion at A, that is, if f of x can be written as a power series on some interval of convergence, then its coefficients Cn are given by the formula Cn equals the nth derivative evaluated at A divided by n factorial. This is the formula we just derived previously. Now, if you go ahead and take this formula and plug it in for Cn, then you can rewrite this theorem in the following way. F of x is always equal to the sum n equals 0 to infinity, nth derivative at a over n factorial times x minus a to the nth power. Why is this important? Well, it gives us a way to find the power series for a function without having to know a power series for a related function. So this allows us to derive a power series for a completely new and unknown type of function. All we have to be able to do this is find a pattern in the derivatives. And many functions have patterns in their derivatives. So the series here is called the Taylor series for a function. And if you let a equal 0, you get a special case of the Taylor series, and this is what we call the Maclaurin series. So in our first example, we want to find the Taylor series centered at a equals 0 for the following function. And note, this is the Maclaurin series because we're centering at a equals 0. And you'll recognize the function. It's f of x equals 1 divided by 1 minus x. Now, I'll remind you that we already know the power series for this function, as we've made reference to it repeatedly in a previous video lesson. However, let's derive it from first principles using the formula for a Taylor series. So the first thing I need to do to be able to do this is I need to write the function in a way that allows me to take the derivative easily. So I'm going to express it as 1 minus x quantity to the negative 1 power. Let's go ahead and find the first derivative of this function. It's going to be negative 1 times 1 minus x to the negative 2 multiplied by negative 1, which is 1 minus x to the negative 2. The second derivative is going to be negative 2 times 1 minus x to the negative 3, again multiplied by negative 1 because of the chain rule, and this gives us 2 times 1 minus x to the negative 3. The third derivative is going to be 2 times negative 3 times 1 minus x to the negative 4 times negative 1, and this is 3 times 2 times 1 minus x to the negative 4. Let's do one more. The fourth derivative will be negative 4 times 3 times 2 times 1 minus x to the negative 5 times negative 1. And this is 4 times 3 times 2 times 1 minus x to the negative 5. So I feel like I can start to see a pattern emerge here, and I think it's safe for me to try to express the nth derivative as a formula. So what do you see here? Well, hopefully you see the pattern developing at the beginning of the derivative here, which appears to be a factorial. So the fourth derivative has 4 times 3 times 2, and we can go ahead and say times 1 as it doesn't affect anything. The third derivative has 3 times 2 times 1. The second derivative is 2 times 1. First derivative is 1, And the original function has a 1 here. So it is safe to say that we have n factorial and then 1 minus x to what power? Well, notice that the power is always negative, and the number is always 1 more than the derivative. So I'm going to express this as negative quantity to the n plus 1. Now, another way to write this would be to say that it's equal to n factorial divided by 1 minus x to the n plus 1 power. So we now have a formula for the nth derivative. Now, what is it that we're trying to do again? We're trying to find the Taylor series, or the Maclaurin series, for this function. Let's bring in the definition for the constants in a Taylor series. So we know that the Taylor series for f of x is the sum of the constants Cn multiplied by x minus a to the nth power. Cn is defined to be the nth derivative evaluated at a and then divided by n factorial. Now remember, for us, a is 0. So we need to take the nth derivative here and evaluate it at 0, right? Because that's what it tells us to do, evaluate the nth derivative at a. Well, that means plugging in 0 for x. So for us, this is going to give us n factorial divided by 1 minus 0 to the n plus 1. And this is n factorial, right? Because in the denominator there you have 1 to the n plus 1, which of course is just 1. So the nth derivative at 0 is n factorial. Now we know that the constants, the Cn's, are defined to be the nth derivative at 0 divided by n factorial. But again, we just found out that this was n factorial. So this is literally n factorial divided by n factorial, which is equal to 1. And so this means your constant Cn is equal to 1 for all values of n. So what is our series going to be? Well, it says that our function is going to be the sum, n equals 0 to infinity, of Cn times x minus a to the n. But we know that Cn is equal to 1 for all n, and we also know that a is 0. And so this is quite literally the sum of x to the n. But we knew that already, right? Because remember, our original function in this problem was 1 divided by 1 minus x, and we know the power series for this function is this series, because again, this is the geometric power series. So what I'm trying to show you here is that finding a power series using this new method results in the same power series. Now in our second example, we want to find the Maclaurin series and its radius of convergence for the function f of x equals e to the x. And believe it or not, this is actually even easier than the last problem. Now, what makes this problem particularly simple is that we're talking about the function e to the x. And we'll just remind ourselves that we're looking for the constants Cn that we can plug into the formula here. And Cn is given by the nth derivative evaluated at a. In this case, a is 0 because we're talking about a Maclaurin series. So the first thing we need to do is find the nth derivative. But again, this is very simple because the first derivative of e to the x is e to the x. The second derivative is e to the x, right? All derivatives of e to the x are equal to e to the x. So when I take that nth derivative and I plug in a equals 0, we are going to get e to the 0, which is equal to 1. And now our Cn's are defined to be the nth derivative at 0 divided by n factorial. But the nth derivative at 0 is 1, and so our Cn's in this case are going to be 1 over n factorial. So our function f of x equals e to the x is equal to the series, right, summation, Cn's, which is 1 divided by n factorial, times x minus 0 to the n. And again, we know it's 0 here because it is a Maclaurin series. And this gives us e to the x equals the sum, n equals 0 to infinity, of x to the n divided by n factorial. And this is the power series for the function e to the x, also known as its Maclaurin series or its Taylor series. Now, what is its radius of convergence? Well, to get the radius of convergence, let's find the interval of convergence. And to do that, we'll take the limit as n goes to infinity of the absolute value of the n plus 1 term multiplied by the reciprocal of the nth term. So what am I doing here? Well, I'm using the ratio test, right? The ratio test is the test that we use to find the interval of convergence. Canceling some things here, x to the n cancels out almost all of the x's except for 1. And then don't forget, if you have n factorial divided by n plus 1 factorial, n plus 1 factorial can be expressed like this. And then the n factorials cancel out. And so this becomes the limit as n goes to infinity of the absolute value of x divided by n plus 1. And this is equal to the absolute value of x times the limit as n goes to infinity of 1 over n plus 1, which is the absolute value of x times 0, which is 0. And this is less than 1 for all values of x. So this means the interval of convergence is minus infinity to infinity. So not only do we know the Maclaurin series for e to the x now, we also know that it converges for all values of x, which means its radius of convergence is positive infinity. This makes it an extraordinarily useful series because it means that we can plug in any value of x. Next, let's find the Maclaurin series for y equals sine of x. Now, just for simplicity here, let me call the function f of x equals sine of x. And remember what we have to do. We have to find a pattern in the derivatives. Now, to do this, we're going to have to do quite a few derivatives here. I'm going to do 6 derivatives, just to really make sure we've established the pattern. All right, so let's go ahead and go through this. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine. And the derivative of negative cosine is negative sine, which is sine. And then the derivative of sine is cosine, and the derivative of that is negative sine. So what I want you to notice is that you start with sine, and by the time you get to the 4th derivative, you are back to where you started. And so we are going to cycle through these functions indefinitely. And let's remind ourselves that the Maclaurin series for a function f of x will look like this: the sum of Cn times x to the n, which looks like this when you write out the first 5 terms. And we'll also remind ourselves that Cn is equal to the nth derivative evaluated at 0 divided by n factorial. So what we need to do next is evaluate all of these derivatives at 0. So let's go ahead and do that. And so here are all of these functions evaluated at 0. Notice that sine of 0 is always 0, so the function, the 2nd derivative, 4th derivative, and 6th derivative are all equal to 0 at 0. And then the odd derivatives are all cosine or negative cosine. And cosine of 0 is equal to 1. So what you should notice is all the odd derivatives are oscillating between 1 and negative 1. So what does that do up here? Well, first, let's go ahead and state our constants. So C0 is going to be 0 because C0 is the function f of 0 and then divided by 0 factorial. So if you want, I could put divided by 0 factorial, but this is still equal to 0. So C naught is 0. C1 is going to be the first derivative evaluated at 0, which is 1, and then divided by 1 factorial. C2 is going to be 0. C3 will be the third derivative evaluated at 0, which is negative 1, and that's going to be divided by 3 factorial. C4 is 0. C5 is going to be 1 divided by 5 factorial. C6 is 0, etc. So when you plug in these values of C into your power series up here, your Maclaurin series, what you're going to get is the function sine of x is equal to C naught, which is 0, plus C1, which is 1 over 1 factorial times x, plus C2, which is 0, right, times x squared, which is still 0, plus C3, which is negative 1 over 3 factorial times x cubed, plus 0, plus, next is going to be 1 over 5 factorial x to the 5th, plus 0, plus etc. So what you should notice is that the only thing you have left are the odd powers of x, because all the even powers of x cancel out since all of their constants are equal to 0. Now we can write this in a more compact form by ignoring all the terms that are zeros. And so we can express this sine of x as 1 over 1 factorial x to the 1 minus 1 over 3 factorial x to the 3 plus 1 over 5 factorial x to the 5 minus etc. And now the only question is, how do we put this into summation notation? Well, let me do it for you, and then I'll explain why it is what it is. So in summation notation, we are going to have negative 1 to the n. That takes care of the fact that it alternates between positive and negative. 2n plus 1 is an odd number. Notice that if you let n equals 0, you get 1. If you let n equal 1, you get 2 plus 1, which is 3. If you let n equal 2, you get 4 plus 1, which is 5, right? So since 2n is an even number, 2n plus 1 is always an odd number. And then the bottom number factorial is the same as the power that you see here. So here we have the Maclaurin series for sine of x. And this will also converge on minus infinity to infinity, just like the function e to the x did. I'll let you verify that by applying the ratio test to this, but trust me when I tell you that it converges everywhere. Next, let's find the Maclaurin series for cosine. Now, this is going to be very similar to what we just did, and so I'm not going to repeat all of the work, but I want to just kind of show you the basic thought process to do this. So what I'm going to do here is go ahead and find the first 4 derivatives of cosine. So the first derivative of cosine is negative sine. The second derivative is going to be negative cosine. The third derivative will be sine, and the fourth derivative will be cosine. And of course, this pattern continues indefinitely. Now, if I plug 0 into my original function cosine, I get 1. If I plug 0 into the first derivative, we get 0. Plugging 0 into the second derivative, we get negative 1. Plugging 0 into the third derivative, we get 0. And plugging 0 into the fourth derivative, we get 1. And we know that the CNs, the constants of our Maclaurin series, are going to be the nth derivative evaluated at 0 divided by n factorial. Now, the exact same thing happened with the sine function, except that the even powers were all the zeros and the odds were all the ones and negative ones. So this is just reversed. So what is the function cosine of x going to be equal to as a Maclaurin series? Well, it's going to be 1 divided by 0 factorial x to the 0 minus 1 divided by 2 factorial times x squared plus 1 divided by 4 factorial x to the 4th, etc. And if you put this into summation notation, we will have the sum n equals 0 to infinity, negative 1 to the n power, x to the 2n divided by 2n factorial. So basically, it's just like the Maclaurin series for sine, and it also converges everywhere. The only difference is, in the cosine function, you only have the even powers of x, whereas in the sine function, you had the odd powers of x. Next, we're going to look at an example of finding a true Taylor series. So this time, we're going to find the Taylor series for sine of x, but it's not centered at 0. It's centered at pi over 3. This is going to be quite a bit messier. So let's go ahead and recall what our derivatives were for sine. Now, what we're going to do for this is we're going to plug the number pi over 3 into all of these derivatives. Now, this is not as nice as plugging in 0. And this is because sine and cosine of 0 is always either going to be 1, negative 1, or 0. But sine and cosine of pi over 3 are not 1 or 0. So let's remind ourselves that the sine of pi over 3 is equal to radical 3 over 2, and the cosine of pi over 3 is equal to 1/2. So for example, when I plug pi over 3 into our function f of x, we're going to have the sine of pi over 3, which is square root of 3 over 2. But then when I plug pi over 3 into the first derivative, we have the cosine of pi over 3, which is 1/2. Into the second derivative, we are going to get negative square root of 3 over 2. Into the third derivative, we will get negative 1/2. Into the fourth derivative, we will get radical 3 over 2 again. Fifth derivative, 1/2, etc. Okay? So now, what is the Taylor series? Well, the Taylor series for sine of x, we take the 0 derivative, which is the function itself, evaluated at pi over 3, so that's going to be radical 3 over 2. We divide that by 0 factorial, and then it's going to be x minus pi over 3 to the 0. So remember, your formula for f of x is a little bit different now. It is the sum n equals 0 to infinity, the nth derivative evaluated at a, which in this case is pi over 3, divided by n factorial, and then times x minus pi over 3 to the nth power. So my next term is going to be plus 1/2 divided by 1 factorial, x minus pi over 3 to the 1. My next term is going to be minus the square root of 3 over 2 factorial, x minus pi over 3 squared. Next term, minus 1/2 over 3 factorial, x minus pi over 3 to the third, etc. I'll only list the first 4 terms here, and then we can simplify this just a little bit. So this first term is just going to be radical 3 over 2. The next term will be 1/2 times x minus pi over 3. Next, we're going to have radical 3 over 4 times x minus pi over 3 squared. And then we have minus 1 over 12 x minus pi over 3 to the third. And again, this continues. Now, if you're wondering how I'm getting this, just keep in mind, I'm just evaluating these factorials and then simplifying this number here. But notice that this is not nearly as nice of a series as the one that we found 2 examples ago. So you can find a Taylor series but the Maclaurin series is typically going to be a much simpler series. Next, let's find the Maclaurin series for the function f of x equals 1 plus x to the k power, where k is any real number. So again, we are going to start by taking derivatives. So our original function is 1 plus x to the k. So our first derivative is going to be k times 1 plus x to the k minus 1. And the derivative of the inside is 1, so I don't need to write that. The second derivative here is going to be k times k minus 1 times 1 plus x to the k minus 2. Third derivative is k times k minus 1 times k minus 2 times 1 plus x to the k minus 3. And we'll do one more. The fourth derivative is going to be k times k minus 1 times k minus 2 times k minus 3, 1 plus x to the k minus 4. So what is the formula for the nth derivative? Well, it's going to be k times k minus 1 times k minus 2 times, where does it end? Well, notice that this one ends at k minus 3, and this is the fourth derivative. This one ends at k minus 2, and that was the third derivative. So it's not going to end at k minus n, right? Because if that were the case, then these numbers here would match. This number here is not the same number. So to adjust it, we're going to say k minus n plus 1. And then it'll be 1 plus x to the k minus n power, right? So notice that the power up here is always k minus whatever the number of the derivative is. So now we need to take these derivatives and evaluate it at 0 because we are looking for the Maclaurin series. So this is going to be k times k minus 1 times k minus 2 all the way to k minus n plus 1. And then when you plug in 0 for x here, you get 1 plus 0, which is 1, to the k minus n, which is going to be what you see here. All right, so what are the cn's going to be? Remember, your cn's are defined to be the nth derivative at 0 divided by n factorial. And so in this case, it's going to look like this. And that's as simple as it's going to get. And so the series here for 1 plus x to the k power is going to be the sum, n equals 0 to infinity, of this and then times x to the n power. And this is an important series. This is called the binomial series. And we can show that this converges on the interval from -1 to +1. We're not going to do it here, but it can be shown. So let's talk about some important Maclaurin series. We have, of course, our geometric series, which we should all be very familiar with. We have the functions e to the x, sine of x, and cosine of x, which we derived earlier in this video lesson. We have the Maclaurin series for inverse tangent, which we actually derived in a previous video lesson. Likewise, for the natural log of 1 plus x, we derived this in a previous video lesson. And finally, we have the binomial series, which we just derived a moment ago. Now, you don't have to necessarily memorize all of these. Of course, if you did, that would be great because all of these are very important series. But I will tell you that these 4 series here are the most important. And it is expected by most teachers that you memorize at least these 4. In the next example, we want to find the Maclaurin series for this function here. But we're not going to do it in the typical fashion that we have been doing problems in this section. Allow me to rewrite this function. So we have 1 over the square root of 4 minus x. Let me factor out a 4 inside the radical. So that's going to give us 4 times 1 minus x over 4. And then we can separate the radical into the square root of 4 and the square root of 1 minus x over 4. And the square root of 4 is 2. And so we can think of this as 1/2 times 1 minus x over 4 to the negative 1/2. And here is the binomial series that we talked about just a moment ago. So I want you to notice that this looks very similar to this, right? We have a 1. We do have a minus here, but that's not a big deal. And then we have a power k, which is equal to negative 1/2. And of course, the 1/2 in front is just a constant. So if I rewrote this as 1/2 and then 1 plus negative x over 4 to the negative 1/2, you could see that we could get this function by substituting in for x, negative x over 4, and substituting into k, negative 1/2. So if we do that, this becomes 1/2, right? That's this number, times the series, n equals 0 to infinity, of k, which is negative 1/2, and then we're going to put n down here. I'll explain this in just a second. And then x to the n power. Oops, yeah, it's not x to the n power. It is what we are substituting in for x, right? We are substituting negative x over 4. So negative x over 4 to the n power. So what would this look like? Well, this is going to be the sum, n equals 0 to infinity, negative 1/2, and then n, and then we have 1/2, so I'm just bringing this inside, negative 1 to the n, x to the n, over 4 to the n. Now, 4 to the n is the same as 2 squared to the n, which is 2 to the 2n. So right here we have 2 to the 2n, and then we're multiplying that by 2 to the 1. And so this is going to give us the sum. And then we have negative 1 to the n, x to the n over 2 to the 2n plus 1. Let's recall that we substituted x with negative x over 4. And we know the original binomial series converges when the absolute value of x is less than 1. So for us, we need the absolute value of negative x over 4 to be less than 1. And this means the absolute value of x over 4 is less than 1. And if you solve this for the absolute value of x, you will find that the absolute value of x needs to be less than 4, which means that this converges for all values of x between negative 4 and positive 4. In our next example, we are going to find Maclaurin series by using Maclaurin series that we know. So in part A, we are asked to find the Maclaurin series for x times the cosine of x. So let's remember that the cosine of x has a Maclaurin series summation negative 1 to the n, x to the 2n divided by 2n factorial. And so x times cosine of x is just going to be x times this series. And since this is independent from n, we can bring this to the inside. So we can move this x in here. And all that does, when we combine those x's together, is it just adds 1 to the power. So we'll have x to the 2n plus 1. And so we get this Maclaurin series very easily. For part B, we know the natural log of 1 plus x has a Maclaurin series summation n equals 1 to infinity, negative 1 to the n minus 1 times x to the n over n. So if we're looking for the natural log of 1 plus 3x squared, notice that we are just taking 3x squared and substituting it in for x. So we can do the same thing with the power series here. We are just going to replace x with 3x squared. So we will have 3x squared to the n. And this gives us the sum n equals 1 to infinity, negative 1 to the n minus 1 times 3 to the n times x to the 2n, all divided by n. So again, all I'm doing here is just taking this power and applying it to the 3, and then taking that power and applying it to x squared, which gives us x to the 2n. In the next example, we're actually working backwards. Suppose we have the following power series, and we want to know what function does this represent. So let me rewrite this. We have the sum n equals 0 to infinity, negative 1 to the n, 2 to the n, x to the n, over n factorial. Since all three of these are raised to the n power, we can combine them as negative 2x quantity to the n over n factorial. Now let me remind you that we know that e to the x is the sum n equals 0 to infinity x to the n over n factorial. So notice that if we just replace x here with negative 2x, and if we replace x here with negative 2x, we will come up with this series. And so this must be the power series representation for e to the negative 2x. In our final example, let's evaluate the integral of e to the negative x squared as an infinite series. So let's recall that the function e to the x has a Maclaurin series summation n equals 0 to infinity x to the n over n factorial. Therefore, we can find the Maclaurin series for e to the negative x squared by simply replacing x here with negative x squared. So we get the sum n equals 0 to infinity negative x squared to the n over n factorial. And we'll rewrite this as the sum of negative 1 to the n x to the 2n divided by n factorial. So now for part A, if I want the antiderivative of e to the negative x squared, I just need to take the antiderivative of the power series. And I think you know how this works by now, so what we're going to do is basically just take the antiderivative of x to the 2n. Everything else stays the same. So we have negative 1 to the n over n factorial, and then the antiderivative of x to the 2n is x to the 2n plus 1 divided by 2n plus 1. And you could leave it like this, or you could simply say this is negative 1 to the n over n factorial times 2n plus 1, and then x to the 2n plus 1 power. Now for part B, we basically want to take the same integral but evaluate it from 0 to 1. So that would be taking the series that we ended up with here in the end, and evaluating it from 0 to 1. Well, that means you need to plug in 1 according to the fundamental theorem of calculus. If you put 1 in here, this is going to go away, and you'll just get this. And then minus, you need to plug in 0. Of course, when you plug in 0, you get 0. So we only need to plug in 1. So we're going to have the sum n equals 0 to infinity, negative 1 to the n, divided by n factorial times 2n plus 1. Now, how do we evaluate that correct to within an error of 0.001? Well, this is when you need to remember that this is an alternating series that converges according to the alternating series test. So if we want the absolute value of the error to be less than 0.001, let's remember that for an alternating series, the absolute value of the error is always less than or equal to the n plus 1 term. And the n plus 1 term is what you get here when you plug in n plus 1. And of course, when you talk about the n plus 1 term, you ignore the alternating factor. So we're going to have 1 on top, n plus 1 factorial, and then 2 times n plus 1, which is 2n plus 3. And we need this to be less than 0.001. So what is the smallest value of n for which this occurs? Well, let's remember that 0.001 is the same as 1 over 1,000. And so this would mean that n plus 1 factorial times 2n plus 3 would need to be greater than 1,000. So when does this happen? Let's pick a random value for n. What if n is equal to 4? If n equals 4, we have 5 factorial multiplied by 2 times 4 is 8 plus 3 is 11. This is 120 times 11. Yes, that is definitely bigger than 1,000. I think I got lucky here. What happens if n equals 3? Well, if n equals 3, you have 4 factorial times 9. And 4 factorial times 9 is not greater than 1,000. So the smallest value of n for which this is true is n equals 4. So what does that mean? Well, it means to approximate this integral to within this error, we need to add up this series from n equals 0 to n equals 4. And when you plug in those first 5 numbers from 0 to 4, you get the following. And this is approximately equal to 0.747. So again, this is really incredible because we don't know how to take the antiderivative of this function. This has an unknown antiderivative. However, we are able to evaluate the definite integral by finding its Maclaurin series and then taking the antiderivative of it and using the fundamental theorem of calculus along with the alternating series estimation theorem. So this problem has a lot of parts, right? We're using a lot of different concepts from different things that we've learned in this course. And that concludes this video lesson.